behind this. Hold on, everyone. Oh, today's it's week 9. I'm really feeling the week 9 vibes so much. I think everyone else feeling the week 9 vibes? There we go. I've managed to switch it off. We're back. Hello, everyone. Welcome to week 9. We are so close to the end. I hope that you are still smiling and still working hard. The break is coming. The big break is coming. So this is pretty exciting. And this is the last week where we're going to learn anything new. Because next week we're going to talk about the exam and then we're going to do some revision. So also for the revision, I am running a poll where you would like to see most of my examples on the revision focused on. So please, vote in the poll. It was in the weekly announcement because then I can better cater the examples to what you need to go over, what you feel is, the bigger gaps in understanding. Barely started the assignment, no smiling. Okay, hopefully you'll get to start the assignment this week. And hopefully it will also be an easier start because your understanding of linked lists is increasing with each lab and with each lecture, I hope. So it will be an easier start, I hope, in that case. But also please remember help sessions and in your lab, ask your tutors questions about the assignment as well so that you can get started. Okay, everyone started last night. Okay, well, that's good. I think the first 2 stages, it doesn't let you vote in the poll. I was wondering why there's 0 votes. What is happening? I will find out what's okay. So this is why there's 0 votes. I understand now. I was just thinking no one wants to revise anything. I will fix that poll up so it lets you vote and you'll be able to vote again. I'll remind you about it tomorrow once I fix it after this lecture. Yep, that would have failed all auto tests. So I'll fix that after the lecture. Thank you for letting me know that. That's how much I want to know what you want to do. No, I really do want to know what you want to do. So I will fix the poll so that we can do things that you actually want to see. Okay, welcome to lecture 15 in week 9. Don't worry about the poll right now. It's going to be in the weekly announcement, but I'll do a separate thing because apparently you can't vote in the one that I've made. Somehow, I don't know, maybe I clicked close voting by accident. It could well be my computer and I are having a moment that is just not a pleasant moment. But I've restarted it, so hopefully that will make it more pleasant. And no tech issues during this lecture, hopefully. Hopefully. We can only hope. Hope and dream. Okay, last week, what did we do? We inserted into a linked list anywhere. We searched through the linked list for specific conditions. We deleted from a linked list. We were just all about the linked lists. That's all that we did last week. And this week, today, we're going to do more linked list stuff, more practice stuff. More things that you can, more practice of those things that we've talked about, deleting, inserting, and so on and so forth, creating. And what I thought I'd do today as well, by popular request, is created a struct with a linked list in the struct to resemble how kind of the assignment is structured so that we can practice all of that as well. Okay, today, so some more linked lists, seeing it inside sort of the structure. I want to look at more boundary cases today. So what I want to do is I actually want to, kind of summarize all the boundary conditions that you kind of always have to think about when you create a linked list. And then what we're going to do today is we're going to learn about some abstract data types. In fact, we're going to learn about one particular type, and that is a stack. So you've heard me use the word stack throughout these last 8 weeks or so. So I hope that it's not going to come as a surprise what a stack is. And we're just going to learn how to implement it. Gordon, results for what? Results for your assignment, results for your labs, results for where? What? Live code today in week 9 directory, so please feel free to follow along with the code. Assignments, we are currently in the process of doing, well, most people, everyone has almost finished their marking, so hopefully we will be able to release the marks towards the end of this week. Yeah, that so far would be a reasonable assumption. But I will let you know if anything changes. And that will be the 2 weeks from when you handed it in. Okay, so I wanted to just quickly summarize as well boundary conditions that you should think about when you manipulate lists, or when you create a list and you are adding things in, you're deleting from a list. The things that you should always be considering is, what happens if it's an empty list? So draw up your example and have a look, decide, will what you're doing affect something if it's an empty list? Most of the times it is. If you're inserting into an empty list, you're obviously adding the head of the list. And if you're deleting from an empty list, well, you can't really delete from an empty list, so it will affect that as well. So always consider what happens if it's an empty list. Consider what happens if the list has only one element, because if you're inserting in front of that element, you're changing the head. If you're inserting after that element, then you know what happens in that case. So consider what happens if there's only one element. If something is happening at the very beginning of the list, because that usually means that you have to change the head of the list. And if something is happening at the very end of the list, so that impacts what you're going to return perhaps, or what you might need to change, what you might need to point to null. And if something will not occur, so if you're searching for an item that is not in that list to insert after or to delete after, so what happens is, you know, you're not going to be able to do anything. So will you do anything? No. How can you check if a linked list is working, especially in the assignment? That is a great question, and that's where you're going to print to your heart's content. That is the way to check if it is working, is to use printf statements throughout the whole thing, or to have a print list, you know, helper function that you use for testing purposes. And you can call it, you know, from and then just delete it when you're finished with it. But lots of printf statements to let you know where you're up to in whichever part you have gotten up to. And when you go into the exam as well, sometimes your function will not have a printing component, but you can insert a printing component to check that it's outputting the right thing. So to check that you're doing the right thing, and then just delete it afterwards. So we often use printf statements in debugging, or like print out what we need to print out when we debug code. And that's really the only way to check if what you're doing makes sense, by seeing it, you know, actually come out onto the screen. Okay, so what happens if we have a linked list within a struct? And this is kind of like what you have in your assignment. So our usual linked list that we've done so far is a single linked list, and it's got a very obvious head, and the head pointer is pointing to the first node, and then the first node is pointing to the second node is pointing to the third node, and if it's at the end, then we point to null. And you've heard me say last week, I mentioned a few times that sometimes you might also have a previous point, so you'll point backwards to a previous node. That kind of linked list actually has a different name to it. It's a double linked list. We don't do them in 1511, so you only do single linked list, which means it's connected in a single direction. You're only going one way. And you can have other types of linked lists as well. You can have circular linked lists, so you can actually go insane when you do them. But we are only just doing a simple linked list going in one direction, which hopefully lets you wrap your head around what a linked list does. So in our linked list, let's say if we go towards that sort of assignment structure, okay, I'm going to switch over to the code and the drawing so I can draw it for you. Lecture slides off. Oh, black screen, and code on and picture on. Amazing. Things are working. Okay, so what happens then? So let's say I have a structure that looks something like this, okay? I have a struct list, and that list inside it has a pointer to the numbers and also a pointer to a struct letters. Okay, so what that means is, let's say I have over here this the blue square in the drawing is my struct list, and I've written list above it, and inside it it's got two more structs, so it's going to have a pointer to a struct number, and then it also has another pointer in here which is to a struct letter. Okay, now let's say I have a struct number, and this struct number, I'm going to say it's the pink boxes here, and a struct number, so this is my number struct, and the number struct inside it will have some sort of data, so an int, and then it will have my pointer to the next number. And so each one of these is a struct for a number, and I'm not going to put in any arrows yet because I don't yet know what's pointing to what. So let's say this is my data, and this is my next number, and this here is my data, and then I have a next number. Okay, great. And then over here I have a struct letter. So let's say the green boxes are my letter structs. So I've got two letter structs, and here I've got a char letter, so it's going to be another data point, and then here it's a next letter pointer. So that's going to be, clearly it's now becoming a linked list because I want to point to the next item in my linked list. Okay, so what I have said here is inside my struct list there is a struct number, and I've called it numbers. So what I'm trying to say is this, my struct list is my main struct, and from numbers I'm going to point to the head. Okay, so what that means is this first numbers here, this is actually where my head is for the numbers list. And similarly for the letters list, this is going to have what my head is for this one. So before this, we always just had the head, you know, is over here, and the head is pointing down, and whatever the head was of the list. But now I'm putting the head inside another structure because contextually, you don't just randomly usually have a head, you have some sort of context around your question. And so if I have a list that has both numbers and letters, my first pointer numbers will be the head to the numbers, and my pointer letters will be the head to the letters. And we'll see it in a second in code as well. So let's have a look. So what I thought we could do is we could do a few functions today just to see how it works. We're going to do one that will create the list. So right now what that means is I'm going to create this structure over here. So the blue box, I want to create the blue box. Then I'm going to create a number, which means I'm going to create some pink boxes. And then I'm going to add a number in. So what that means is I'm going to link it up into my linked list. And I'm going to print some numbers just so that we can see it working. Because otherwise there's no way to really know whether what we've done actually makes sense or not. Okay, someone's asked time frame for our exam. Your exam is 1 till 7 p.m. on the 3rd of December. Okay, and then I've got here, you can see if you can create these bottom two after the lecture, just using the code that we've done for the numbers to see if, you know, get some practice to see if it's working. And I've got a main here just to practice everything that we're doing. The main is very simple. I'm just calling the function add number to add in some nodes, and then I'm calling the function print numbers to print out the nodes. But the first thing that I do is I create the list. So the first thing that I'm doing is I'm creating this blue box over here, because once I create the blue box, I will have a head pointer to my numbers list, and I will have a head pointer to my letters list as well. So once I create the list, I can actually start adding things in because I will know where the heads are. So let's do this struct list create list. So we're having a function called create list, and that function will return a struct list pointer. So what it will return to me is the address where that struct list is sitting. So the address of the blue box here. Okay, allocate some space to the list. How are we going to allocate some space to the list? And think I'm just creating the blue box. And the blue box currently has, well, I've got nothing much in there. Nothing is pointing to anything. So, yep, that's right. So we'll malloc some space for our list. So I want to malloc struct list, and I'm going to call it new list, and it returns a pointer. So I've forgotten my star for a pointer. So struct list new list. So I'm going to store the address of my malloc return inside this new list pointer. I'm going to malloc size off and struct list. Okay, so what that will do is it will create this box here for me, the blue box, no arrows, okay? But it will give me some space, and it will return for me the space where this one starts. So in my new list, this is going to be my new list pointer. And this new list pointer will have the address of this list. So let's say this list is 0xAAA. So this new list is going to hold the address of it. So as long as I have the address of this new list, I'll be able to access the headers for my numbers and letters as well. Okay, so I've created some space for it. I now know where this list is sitting. So now I want to initialize it. Okay. So I've got two things inside my struct list, and they are a pointer to numbers and a pointer to letters. So to access them, I'm going to say new list, pointer to the numbers. And right now, I don't have any nodes. There's nothing there in either list. I only have the blue box, which means that both of these will be set to null. But it is very good practice to initialize them as opposed to just leave them with nothing there, because it means that you've thought about what you're doing and you've filled in the gaps. So my new list is, spelling mistake, letters, and that's also equal to null. Okay, and then I'm going to return the new list back to my main function. Okay, so Neil, excellent question. Does the blue list already exist because of the struct declaration at the top before the main, and does that make it the head? Okay, so, and thank you. Excellent, semicolon forgotten. Thank you very much. Okay, so the blue list, I've got the struct for it, but I haven't used it anywhere yet. So when I have this struct, I've defined it, but because I haven't used it anywhere yet, I haven't declared it, I haven't done anything, it doesn't actually exist per se because I haven't asked to use it. When I malloc some space for it, what I've done is I've actually created that box, and I'm ready to fill that box in. Okay, so let's now add some numbers. So now at the end of this, I have stored the address in list start. So that means that this address here is now inside this list start pointer. Okay, so add some numbers to our list. I guess we need to add some nodes in, and I'm going to just add the numbers part of it in, okay, to show you how it's done. So what am I giving to my function? I'm called the function add number. I've given it this list start. So what I've given it is the address of this blue box here, and I've given it what number I want to put in the node, okay? So let's do that. Okay, so add number. Let me just increase this so that it doesn't go over. Okay, so first of all, make the number node that you will be adding in, okay? I said struct number, new number, and then I've called this function called create number. So what I'm doing with the number in it. So what I'm doing is I'm actually making another function that it will create the number for me, which means that all it will do is create this node. So what it's doing is creating the pink box for me and filling it in with whatever data I want to put in it. So creating the number with the number, I've got a new number. I've malloc some space, which means I've now drawn up my pink box. And now I want to initialize it with the data that I have. So I've sent to that function the number that I want to go into this node. So that means my new number data is going to be equal to the number. So it's going to be equal to this number that I gave it here. And that means that the number 1 will go into it because that was the first number I called. And then I'm going to, and then I don't need to do anything else, okay? Because, oh no, I do need to do one more thing. What do I need to do? Where I've just said above, it's good practice to do it. Who can remember what's good practice to do? What's the other element of my struct that I need to say something for? So I've now filled in this, but I really need to fill in this. So what will be my next line to create this number? Yeah, so I've got to set it to null. That's right. So my new number, next number, is going to be equal to null. So that and that is going to be equal to null. Exactly. So what happens now is up here, when we've called add number, list start 1, and then I've gone down here, I've said create number. What I've done is I've created one of these pink boxes and I've just placed 1 into this box, and what I've also done is I've placed null into it. So this is what I've now created. This node here that is just floating about, okay? Okay, so now I really need to add it into something. Okay, and this new number is now storing the address of this node here. So let's say this node that I've just created is an address, and my pointer new, and I'm just going to erase this so it doesn't throw you off. So my pointer new number, it is holding the address of this node that I've just created that's not connected to anything. And I don't yet have this connection either. So I'm gonna get rid of this arrow for now. So far I have this new list sitting in OXAAA. I've got a new number in OXBBB, and this node is floating about. Theo, why is it next number and not next? I just thought in this example it is a better variable name. It can be called whatever you want, but I just thought because I have letters and numbers, I just broke up the next just to make it more obvious what's going on, but it can definitely just be next. I was just trying to be more obvious in the example of what it means. Okay, so now create a current pointer to keep track of where we are in the list and set it to the head of the numbers list. Okay, so I want to do my usual business where I create a current pointer and I'm going to set it to the head. Okay, so struct and my node is of type number. So struct number, and I'm going to call it current. Okay, now where is the head of the list? The head of the list is actually inside my list. And what was I calling it? So inside here, so list start. So the head is inside this list start. Inside the numbers, that's going to be the head of the list, okay? So that means that the head of the list is inside my list start, and it is located in the numbers element. That holds the address of the first node with numbers, which means that it holds the head of the numbers. Okay, and now let's have a think about those boundary conditions that I just talked about. So, and one of those boundary conditions actually applies to me right now, because what if there's no other items in the list? And my list is right now empty. I don't have any other items in it. There's no arrows, there's no connections, there's nothing. I just have a floating node that's somewhere in space that's not connected into this list at all. So my first boundary conditions is really considering what happens if there is no other items and I'm adding the first item in, okay? Which means that that will really be the head of the list. how do I check if it's an empty list? What will be my decision here? How do I check if it's an empty list? If I know that this is the head, how do I check if it's empty? Yeah, well done. Well done. Well done. So if current is equal to null, that means my list is empty, okay? And that means that I'm adding the first element into the list, okay? Which means that my list start numbers, so that means that's my head, is going to be equal to this new number. Or, I mean, you can say that this is just current is equal to new number because that's what it's pointing to. So let's just do that so as not to make it confusing. So then that means that current is going to be equal to the new number that I've just created. So now that means that this address in here in this numbers pointer holds the address that is, so it holds this address here, which is 0xbb, which means that I've now said that this here is my head of the list. So I've hooked it in and I can come out because that was where my connection has occurred. So I'm going to return 0, which means I'm going to return back to my main function. I've added it in. Okay, otherwise I'm going to insert at the end of the list. Okay, how will we get to the end of the list? How will we get to the end of the list? How will I know I'm at the end of the list to insert? What will be my condition? What will be the loop condition? Yep, so you're saying while current is not equal to null, okay? While current is not equal to null, okay? That means what I will do if I go to current is not equal to null, then that means when I exit the while loop, if I do this, I keep typing somewhere else where I'm not meant to type, okay. If I do this, and this is another good example of what's going on, when I exit over here, this while loop, then current is definitely equal to null, okay? Because whilst it's not equal to null, I'm going to be going to the next number. So when I exit the while loop, that means I am going to be equal to null, which means that it's too late to insert anything because now I'm at a null pointer, okay? So in fact here, it is better to go to current next is equal to null because what that will mean is you will stop at the last node, okay, as opposed to going past it. You will stop at the last node because the next of that node is going to be pointing to null. So you're going to stop at the last node as opposed to going past it. Okay, so we're going to go current to next number is equal to null. Current is equal to current next number. So all I'm doing in this loop is I'm going to the end of the list, okay, and stopping at the last element. So that means when I come out of this while loop, it means I am standing, sitting, I am somewhere hovering, I'm standing at the last node, on the last node, haven't gone past it. I haven't returned 0 yet. Oh, I'm not returning 0 in the if statement. This return 0 is past, the if statement is over here. This is just a while loop. This is just to return 0 at the end of the function. It's not inside the if statement. Okay, great. I'm now at the end of my list. So now what I want to do is I want to insert. Oh, you mean this return 0? Okay, Tom will explain it. Because. Yeah, it's basically because I've inserted here at the head, I've inserted the first element, so I'm done, which is why I can return back to the main. Okay, so I'm standing at the last node on the last node, and I want to insert after this node. So this node that I'm standing on, which is my current node, I want to hook it up to that. I want to hook it up to the next node. So what am I going to do here? So that means that I'm going to say that my current node that I'm standing on, the next right now will read null. But what I want to actually do is I want to hook the new node in to it. So the new number is going to be the new pointer on the next. And for good practice, I will say that my new number next, even though it's already set as that, I'm going to say it's equal to null, okay? Because that means that I've filled in both of the elements of that node. Okay, so that will add the node in, whether it be at the head or will be at the very end of the list. Okay, so that means I've added these nodes in. Okay, fantastic. And now I want to just check that everything is working. So I'm going to create a current pointer that will again point me to the start of the list. So current number, struct number current. And you've already said that it's going to be list start, which is the list that I've given it, but the head is sitting inside my numbers pointer. So list start inside the numbers pointer is the head of my numbers list. And then, you know, we work with it the same way. So it's nice to be able to have that current, because if you have something, you know, long here, you don't have to write it each time. You can just write current as well. Okay, so let's see what it does. Let's see how it works. Yeah, so Catherine, that's right. So what I was saying, so new number, next number is already initialized to null, but it's good practice to just, if I've got two elements, I'm going to fill them out here just to make sure that there is not a mistake somewhere else. It's good standard to just, I've got two elements in my node and I'm going to set both of them. And it means that I'm thinking about them in that same moment in time. So I'm making sure that everything is in order. So cleaning house, basically, which I don't really do that often. But okay, here we go. DCC. I forgot what we were doing. Letter number. Yeah. Okay. Letter number.co. Letter number. I shouldn't call it something so long. Okay. So I was adding 1, 2, and 3. And let's see. And it's printed nothing because I've done something wrong. Let's have a look what I've done wrong. Let's see what I've done that doesn't quite fly. List start numbers. I've got a struct number current. Where have I gone wrong? Have I added all the numbers to the list? I've added at the start 1, 2, and 3. And I'm printing the list here and I'm giving it list start. Okay. And here, have we added it in properly? Let me just, okay, can anyone see my mistake? I can't see it yet, but I'm searching. Okay, then I've created a new number and I've created the number, which means I created an empty one. I gave it back with new number. Got a current. In your print numbers, is it meant to be current data? Yeah, because current is list start numbers data. Let's just check my struct. I do have a struct called but, and then I'm moving along correctly. Current is equal to current next number. So I've moved along nicely too. Where have I stuffed up? Current next number is equal to new number. Yes. New number, next number is equal to null. Yes. Have I linked start numbers to numbers? I thought I have. This was working when I run the code before I do it in the lecture, so I've made a mistake somewhere where I was typing. What else? Yeah, okay, so I haven't, let me have a look. Have I stored the new number in the list? Struct, have I done that? Let's have a look. Oh, I have not. Yeah, okay. Yep. Sasha. Rookie error. Okay. Draw it out. I love it. I love it. Absolutely. You should always draw everything out. But I think I haven't stored the new number in the list struct. Let me just, and you know when you just look at it for a really long time and everything start to blend in all at the same time. Okay, so I've created the number. I've sent the number back. Now have I added it into my list struct? New number, create number, list start numbers. And yeah, this is the problem. Okay, this is the problem right here. I'm just going to do this. List start, because my list start is actually the start. This is the problem. So if my current is equal to null, it's what I was doing before. Then my list start is equal to new. My list start numbers is equal to new number, because I'm printing from the list start and I haven't linked in the new number to the list start. It was only to the current. I'm back. Okay, everything is okay. Let's try it again. Here we go. Yes, much better, much better. Does it make sense what the mistake was? Let me know if it makes sense what went wrong. Yeah, Ray, as you said, exactly. I haven't linked in the head, but does it make sense where it was? Yeah, okay, good. All right, excellent. Okay, very good. So that's kind of how the assignment is structured. I'm going to do another example today in the stack using the same theory so that you get even more fun practicing it. And I hope this one makes sense. See if you can do it for the letters as well. And this is quite really similar to how your stage 1 is structured as well. So I hope that, you can kind of apply these skills to the stage 1 of the assignment as well and get through it, fairly quickly. And well done, noticing what was wrong as well with the code. Okay, I'm just going to switch back to the slides because we're going to start talking about abstract data types. Okay, so abstract data types. Has anyone ever heard of abstract data types? Anyone heard of abstract data types? So much excitement. Please just hold the excitement. If you haven't heard of it, that's okay. You've been using them because abstract data types are basically data types whose implementation details are hidden from the user. Okay, so what that means is basically, let's say we have a stack, okay, and you know how a stack works. Maybe you do, I'm not sure. We're going to talk about it in a second. But I don't care how that stack is implemented. The stack can be implemented using linked lists, or using arrays or using other data structures. All that matters is that the rules of the stack remain the same, but I don't care about what kind of implementation is there. So what it means is that, whoever's using our code doesn't need to know how it was made or how it was implemented, but they know how to use it because an abstract data type will follow certain rules. So for example, a stack, the lovely stack, and here's some plates because it's just a good example of it. And then I was like, my plates are also stored in that plate holder, which makes it an even better example of a stack because I cannot lift out plates in the middle. All I can ever take is a plate from the top. So a stack operates in a last in, first out structure, which means if I make a pile of plates, I can only take the top one, even though the top one is the last one that I put in. And that's how a memory stack works as well. So you make a pile, you stack things onto the pile, and then you can only remove the top thing one at a time. So you only ever remove from the top of the pile. So you can put something on top and you remove something from the top. And basically just think of a stack of dishes. I had a stack of laundry before that, but you really can remove things from the middle of the laundry, but the plates is much harder to do. Okay, so for example, let's see, let's say we have this little piece of code, and this is how the memory stack works for functions, okay? Because remember how the memory is also divided into the stack and the heap. Well, the stack works it's called a stack because it works like a stack in that it's whatever goes on top, that's the first thing that gets removed. So you're not really removing from the middle ever. So let's say you have this function here, int main, you've got int number 13, int new number, and don't worry about what, really it's doing. It's really just to see the functions. So when my main starts running, the main goes onto the stack, okay? Then, and this is just for functions. Other things go on the stack like variable names, but this is just for functions. So then I say new number is equal to new number plus square number. So I've just called another function, which means my square went on top of this stack, okay? This means that I can only now access the square function. I'm not looking at the main. So now I'm sitting inside the square and I go int change number is equal to change number. I've now called another function from here, okay? And now that I've called another function from here, that function moves to the top of the stack and only this function is now accessible, okay? Then I go inside here, I return number plus 1. As soon as I return to the place where I was called from, that change is taken off the stack. So now I'm back with only having a main and a square on there, with square being the only accessible one. And as soon as I return from my square function, so as soon as I return something from here back to the main, the square is popped off the stack, and now I only have the main left. And then when I return 0 and exit out of this function, this is popped off the stack as well, and I now have an empty stack again. So only the top element is ever accessible when you're playing. And playing, I don't know. When you're playing, I really want to say when you're playing with stacks, but a stack is just that. It's an idea of how something works. It's a set of rules that must be followed, and then it's up to us how we're going to implement it. So can you actually think of anywhere that a stack is applied, like on your computers that you've done in your everyday interaction with computers? There's lots of examples of a stack being implemented. Can you think of any? Pop them in the chat if you can think of any ways that a stack is implemented. And so it behaves in a certain way. It's defined by a certain set of rules. Today we're going to implement it using linked lists to give you more practice with linked lists. And I might also do it using arrays just to show you that it's possible to do it with arrays as well. So folder structure, where you're only moving one across and only the top element, you're only going back once. Excellent. What about also your back browser window? Every time you click back, you're only going to the top one back. Undo, redo in Word as well is often done with a stack as well. So there's quite a few ways in which you solve problems, and something like a stack becomes quite useful because the top thing in is the top thing that you're popping off as well. So because a stack can be implemented in any number of ways, and today we're going to try and do 2 of those ways. We'll implement it with linked lists and we'll implement it also with arrays. I'm going to show you why it's useful to have multi-file projects as well. Why not? We might as well just use that as well. So we have one header file, okay, for both implementations. So let's say I'm the company that is, going to program this out, and I'm going to have a, I've given a header file to a few programmers, and it's up to them how they're going to implement my stack, because my header will remain the same, and then we're going to actually compile once the header with the linked list structure, and once we'll compile the header with the array structure as well. So basically, it doesn't matter as long as you follow the rules of the stack. Okay, so there's some special terms for a stack, and basically to put something onto the stack, you push it onto the stack, you add the element on, it's called pushing. And when you take something off the stack, you're popping off the stack. So you're gonna, pop things off, push things on. We're gonna look at a few functions. We're gonna create a stack, then we're gonna add to the stack, so we're gonna push onto it. We're gonna take from the stack, pop off the stack. We're going to just quickly do how many things there are in the stack, because that could be a useful function. Why not? We're going to destroy the stack. And one that I don't have in there, but we will need to have, is print the stack, because otherwise we won't know if what we've done is correct or not. We'll have one header file, stack.h, and we're going to have two implementation files, one using lists and one using arrays. And that should hopefully be able to... And that should hopefully be able to cover us off, and to show you that there is different ways to implement things. Also, more practice doing linked lists. Okay, so I think now would be a really good time to have a break before we start implementing. Let me just go to a break slide. And then I'll still remain... Oh, got a bit excited. And then I'll draw up the stack afterwards. Okay, let's have a 5-minute break. I'm just going to do that because that's faster than me leafing through. Okay, we're going to have a 5-minute break, and then when we come back, we're going to implement the stack. It's what all your dreams are made of. All right, just started talking and I forgot to actually unmute myself. So let's try this again. Yeah, welcome back. Gordon, yeah, you can do it in any way that makes sense to you, because there are many different ways in which you can solve these problems, and you should adopt the path that works the most for you, as long as you consider those boundary cases that we've talked about. And as long as you split it up in a way that makes sense to you. You don't need to create a number in an outside function, but it makes sense to me to do that because then I'm splitting up the functionality in a way that makes sense. So yeah. Okay, I'm pasting into the chat a solution to the horses problem. If anyone is interested, you can go have a look at that. Christian is just, don't kill the horses. They're so cute. Okay, and let's come back to, I'm going to pop those off. I'm going to put my camera back on. Okay, let's talk more about the stack. Okay, so it took me a while to remember what we were talking about, even though it's only been 5 minutes. Let's say I have a stack, okay? And okay, so this over here is my stack. And if I want to do a linked list implementation for that stack, then I would create my container for the stack, and then I would start to fill in the container with whatever numbers I want to put into it. So basically, let's say I want to put the numbers 1, 2, 3, and 4. I'm super creative with my numbers, if you might have noticed. What I'll do is I'll create a node for 1, and I'll pop it in here, so that's going to be my 1. Then I'll create a node for 2, okay, and then I'll pop it on top. So now only 2 is available to me. So 1, and 2. Okay, then I need to do 3. Okay, so then I'll do a 3. Okay, so then the next number will be my 3. Okay, so I'll pop the number 3 in. And finally, I will pop the number 4 in. So almost ran out of space. Okay, then 4 in. So now on the top of my stack, I have the number 4. So if I've pushed on, so I've pushed on 1, so my code will kind of look like I've pushed on the number 1 and it's gone onto the stack. So push 1 onto the stack, I've pushed on 1. Then I'm going to push 2 onto the stack. And when I push 2 onto the stack, it goes, puts a 2 on. Then I'm going to push the 3 onto the stack. And it will push the 3 on. And if I push the last number onto the stack, then it will push the 4 onto the stack here. Okay, then if I start popping, okay, once I start popping, okay, pop, and what I'll do is I'll pop off a certain stack. I don't say what I'm popping because I always pop the top number. So my first pop will give me a 4 because that's the top number in the stack. Then if I pop again, I'm going to get a 3 because that's the next number in the stack. So now the stack will only have 2 and 1 left in it. So then if I pop again, I'll get the number 2 because I've now popped off the stack again. So now the stack only has 1 number in it. It's got 1. So if I pop again, I'll get the 1, which is the top number in the stack and the only one. So now the stack is empty. Okay, I've got no more elements in my stack. So that's kind of how a stack works. So the last one in, first one out. Okay, so let's see if we can write some code for it, implement it, and use the code to kind of with a linked list implementation. Okay, so let's look at the main. So in the main, we have something, and it's going to be very similar to what we've just created, the structure that we created before. So Faisal, can you only pop 4 before 3? That's right. I can only ever pop the top thing in my stack. I can't access anything underneath. I can't pull out the middle plates, only the top one ever. So anytime I pop, it's just going to give me what was last put on the stack. So I'm going to create the stack first, which is me creating this lovely container here, so the blue container. And we're going to do the code for it. I'll draw it up as we code as well. And then we're going to push some numbers onto the stack. So I'm going to push onto the stack. I'm letting, obviously, my function know which stack I'm pushing onto and what number I want to push on. So I'm pushing 11, then I'll push 12 onto the stack. I'll push 13 onto the stack, and I'll push 14 onto the stack. Then I'm going to print out the stack so that we can see what's going on. And then I'm going to do some popping. I feel like we're doing a dance. Just pop, 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 pop. Okay, that was completely off digression, tangent. Okay, popping off the stack. So I'll pop one thing off, and then I'll pop the next thing off. So if the last thing I put on was 14 onto the stack, what that means is this first pop will result in a 14 being popped off, and my stack now having 11, 12, 13 in it. And when I pop again, because the top of the stack is now 13, it'll pop 13 off, and my stack is now going to be 11 and 12. So I've got my main function. So now let's go to my list implementation. Actually, let's look at the stack.h first, which I wrote a lot in. I'm sorry, but I was trying to make it more clear what's going on, but now it just looks like I wrote an essay for you. This is the header file for the stack. So this has all of my different functions inside it. Okay, so the first thing is a create stack function, and this create stack function creates this blue container for the stack. And it's going to return to me the pointer address of that stack. So it's going to return to me the address of that blue container. Where have I created it? Okay, then I'm going to push onto the stack. When I push onto the stack, I don't return anything because all I've done is just added a number in. I don't need to return anything. But what I'm going to give my function is I'm going to give it the stack that I'm pushing onto, and also what on earth I'm pushing onto that stack. So the actual, it can be a character. The stack doesn't have to be just numbers. It can be a character. It can be an array, again, because you're creating the struct for the node. So it can be anything as well, but it's just easier to show it with numbers. Pop off the stack. Okay, when we pop something off the stack, it does return an int because it returns the number that you have popped off, and you have to give it the stack that you're going to be popping off. So you're going to give it the stack from which to pop the number off. Okay, then I've got a few other ones just to show you that you can have a whole bunch of different functions associated with the stack. One of them is just a size of the stack. So if you want a quick access to how big your stack is, you will return the int, so the number of things in your stack, and we will also give it the stack which to count up the numbers of. We're also going to implement a destroy stack function this time because that is also useful for your assignment, because otherwise you're going to have this random empty stack floating about that doesn't really need to be if we want to finish up with it. And finally, spelling mistake. Finally, we want to have a function that prints the stack so that we can see if what we're doing is correct, if it's pushing and popping as we want it to be. So we're going to print the stack again, doesn't need to return anything, but we give it the stack that we want to print out. Okay, so let's go to our stack list and let's think about how we can define each of the elements. Okay. So how do you think we need to define the stack itself? Okay, so we'll have a struct stack, and I'm going to define it here. And I want to always be able to know what is on top of my stack, and what else do I need to have for my stack. And again, based on what you're doing, you might slightly change the definition of your stack. It's not set in stone. You are in charge of your own destiny. But the things that I want to know in this particular stack is the top node, and so Sienna, the size would be very useful as well. So I'm going to say the size of the node, and the other one is I want to know what the top node is, because that's the node that I'll be popping off all the time. So I want to be able to quickly access the top node. Okay, now my node, because I'm just making a stack of numbers in this case, so my node is just going to be the same one that you always use in a linked list, so something that you're very familiar with. So it's going to have an int data, and also it will have the pointer to the next node. So struct node next, because that will give me the ability to link them up to each other and create that linked list structure, because I'm implementing using a linked list. Okay, so we've talked about it before. So what happens if we're creating the stack? We've said that in the header file, you can see the definition. If I'm creating the stack, it's going to be of type Struct Stack pointer. So I'll copy that across, and I do not need any input because there's nothing to really input when I create the stack. So it's a void. Okay, so let's create our lovely blue container to start with. Okay, so what I want to do, how about I move across so that we can draw it up as we do it. Okay, so what I want to do first off is I want to create my blue container to start with. I want to just create this stack. Okay, so an empty stack. I want to allocate some memory to the stack structure. Okay, we're starting to get pretty used to how to do that, aren't we? We're starting to get pretty used to what's going on when we do that. And what we want to do is we really want to malloc some space for it and then return where we've given it some space. So let's malloc some space for our stack structure. So struct stack, and we're going to new stack. Why not? And remember, you can call these what you want as long as it makes sense as well. So struct stack new stack, and I'm going to malloc some memory for it. So size off. I think my spelling is getting worse and worse as the weeks go on. I can't decide. Okay, so that will allocate some memory, and what will happen, let's say I've created some memory here. It's sitting at AAA. What that means now is my pointer new stack is equal to this memory address here. So now I know where I've created this memory container, so this stack container that will house my linked list inside it. Now, what is the first thing we should check for? Okay, when I'm mallocing some memory, it's quite good practice to check that actually there was enough memory that I could store things in. So let me delete. So what I want to do is I want to check that malloc has actually worked, that there's been enough memory, because otherwise if I try and go on and there wasn't enough memory, then I'm just going to try and access null pointers all the time, and it's going to just throw everything off. So it's really important to check if there was enough memory to create the structure. So what I'm going to check is I'm going to see if new stack is equal to null, because that means there wasn't enough memory space. And it's returned a null pointer if it didn't have enough space. So if it's equal to null, there's not enough memory to create a stack. And for the first time ever, probably you've seen me use this exit here. Has anyone seen exit used before? And there's a reason why I'm using an exit. Has anyone seen the exit? No. Okay, I'll explain why I'm using it. So my function over here returns a struct stack pointer. So if I try to return 1 here, okay, if I type out return 1, that's not going to work, because returning 1 is returning an int. So what exit allows you to do is it allows you to break out of here and return back again out of the program. Now exit is inside this standard library here, hash include standard library.h, and what the one here in brackets means is exactly the same when you return 1. I'm saying that I'm exiting out with an error. So it's not a successful exit out of this function. It's an exit with issues. And you don't really need to know where the issues go, but just the exit 1 is an indicator for when you're trying to debug things afterwards. The 1 will tell you that you exited out with problems. So basically, I have to use an exit 1 in here because I can't really use a return because I need to return a struct pointer, but an exit allows me to return without a type. Okay, so we've checked. I haven't actually checked. What happened here? Oh, I've gone down to the wrong thing. Okay, here we are. I'm here. Okay, I've used exit again, clearly. Okay, so exit 1. Now, I need to initialize the stack that was created. Okay, so I've got this lovely stack here, and there's 2 elements in my stack. There is the top node, and so I've got my new stack top, and I also have my new stack size. Okay, what will they be equal to when I initialize? And remember, good practice to just initialize everything in this node, anything in this structure. So what will my top be and what will my size be? What do we reckon? Once we've created it, so we've just got a blue container, what will either one be? Sean, great question. Should we also do the checking thing for the linked list? So in your assignments, you will often be told you can assume that nothing, that it's not going to be ever. But when you're mallocing space, you should check that it's not return a null, because otherwise you will not be able to go on with any of your program. So it is very good practice to check that there was enough memory to actually create the structure that you want. Okay, so the top, you're right, is going to be equal to a null pointer. And what will the size be? What is the size of my lovely stack over here? How many things have I got in my stack right now? How many things have we got in the stack? Not many. Even none. Yeah, well done. 0. We've got 0 items in the stack, so we're going to give it a 0, a size of 0. My indentation is really off today. I don't know why either. Okay, anyway, so now we've got, and then we return a new stack back to our function. So what that means is we now have this line here in the main, struct stack, new stack, create stack. We've now created this lovely container that is ready for action. It is ready to have numbers pushed onto it. Okay, so now let's look at the pushing function so that we can see how we can implement it as well. So let's have a look. So push stack, and we're giving it the stack onto which we want to push, and we're giving it the element that we want to push onto it. Okay, so push stack, and in our stack.h, we have defined push stack to return nothing, but to give it a struct stack and an int item as well. Catherine, yes, is function void the same as function with empty brackets? It is. So my function is returning void, and it's getting, I saw there's another question, Dove, what if we do not define top is equal to null and size is equal to 0? Then you're going to have an uninitialized, if you try to access it afterwards and do something with it, it's not going to be initialized. So remember, when we declare our variables, we also initialize them. And that's, better code, better style, better everything, and better logic as well when you have initialized it. When we define functions, do we have to have that void? Very good question. I always like to have void because it's telling me that I've thought about it and I've decided it is void. Okay, so then I have a struct stack in here. And I have my int data that I will be pushing onto the stack. Data, have I called it data? What did I call it? Data. Okay, should I call it something else so that it's obvious where things are coming from? I'll just keep it as data for now. Okay, first thing we do, allocate some memory for the new item that you will push on. Okay, so what are we doing here? Oh, well, we're creating a new node, aren't we? Okay, so let's create a new node. So we want to malloc some space for it. Let's say this is my new node. So I've created this new node. let's say the address of the new node is B11, and I want to store new node, and that's going to be equal to the address. Okay, so my pointer is going to have the address of this new node that I've created, so line 46. And now I want to check if there's enough memory to make a new node. So now I'm really underlining that you should really be checking whether or not you've got enough space. So I'm going to check again if new node is equal to null. That means that there's not enough memory to create a node, and you exit out of this program. And again, exit is useful to use here because I have a void function. I can't actually return anything out of it. So, okay, now I want to initialize the new node. So right now my new node is empty. It's got nothing happening for it, but I want to place whatever this data is inside my node. So I want to create it here, and it was, I can't remember, what was it? The first one was 11. So I want to create something that will have 11 in here. So to initialize the new node, it's int item in here. I'm going to change it to int data. There we go. Okay, so to initialize it, I'll have my new node, and inside the data element of the new node, I'm going to place, and this is what I mean. Does it make sense that this is the data that I'm placing here? Or should I have it as item to make it more obvious? I'm going to move it to item to make it more obvious what's going where, so it doesn't get confusing. Okay, so I'm going to have this, whatever I've sent it, so the 11 is now going to be inside the new node data, which means that I've now placed 11 in here. So now the only thing I need to place is my lovely next pointer. So my new node next. And that's going to be equal to what? Where do I want to add this new node if I'm pushing onto the stack? So think about when I'm pushing onto the stack, I always want that last item to be the head. So in a stack, I'm always inserting at the head, really. Catherine, new node number. No, because I've got an int data here. So that's why it's new node data. Okay, so if I want to go to the top, first of all, I want it to be my top one. Then I'm going to say my stack top is the one that's going to hold. Okay, so I've pushed onto the struct stack S, okay, which means that my S is going to be on the top here. So what I'm saying is that I want this new node to go inside here, okay, and I'm saying that my stack, which is called S, the top element of my stack is actually this node over here. Okay, so now I know which node is always at the end. Yeah, so we're always inserting at the front, at the head. Yeah, that's right. Okay, so we've got our first element inserted in, and what should we do now? We've got to correct our stack by changing the top of it, so the head and the size as well. So the size is easy. If I've inserted something into my stack, that means my size is going to increase by 1. So I'm going to say my size is going to increase by 1. So I've added an item in, which means that I'm going to increase by 1. And my top node is going to be equal to the new node. Struggle town with writing. Okay, so what I've done here, so my new node next is now pointing to whatever was at the head, and my head is now the new, oh goodness gracious, no one's picked up this erroneous use of an arrow. Here we go, new node. Okay, so that should do it. That should push something onto the stack. Should we pop off the stack? Who wants to pop? Anyone? Okay, let's pop off the stack. Even if you don't want to, I'm going to make you pop off the stack. Okay, let's think, first of all, so we're popping off a number, which means we're going to return the number that we're popping off, and we're going to pop off a particular stack. Okay, boundary case first. What happens if the stack is empty? This means that there is nothing to pop off. What do you reckon will be, what way can we check if it's empty or not? What gives us the size of our stack? How can I access and check if this stack is empty? Yep, so if size is equal to 0, so size is an element inside my stack S. So I'm going to access the size element. And okay, not quite, Neil. Good guess that it's S top is equal to null, but remember that the top one is actually a whole node. So my node is not, it's really the size. So if my size is equal to 0, because we're keeping track of the size, so if my size is equal to 0, then there is nothing in this stack, which means that there is nothing to pop off the stack. So stack is empty. And if you notice here, I can return 1 again because my return is an int, so it's fine to return 1. And now I want to change the top node in the stack to prepare for popping the head off as well. Okay, so let's see what happens if we do that. Okay, so let's say I've got, I'm going to just add another node just to demonstrate what happens, and then we'll talk about. So let's say I've pushed on 12 as well, and I've pointed it down to this one. Okay, let's say I'm going to pop off 12. Okay, so, well, I have to pop off 12 because 12's at the top. Okay, and then S top is now moved up as well if I've got the 12 in there. So this is my top, and my S size is 2. All right, so what do we need to do if we're going to pop off? What do you reckon needs to happen? So first of all, our S top is going to have to point to the node that comes afterwards. Yeah, so we're going to need to change that. And so I want to really, a few things I want to do. So I want to move my top to the one that's next. So I want to move it to my S top next. What that will do is it will move this down 1 to point to the lower node. Okay. But before I do that, I should probably save this number that's happening here. I want to know what number I'm popping off. Okay. So how can I do that? And I've called it int popped number. So if I have my int popped number, how can I access it? What do you reckon? How can I access this number 12 here? Who's with me? Is everyone still awake? I hope so. I'm sorry. I know it's all too much for week 9. Yep, so we want to access the data component. So I want it to be inside S, top, and my data component. That's going to give me the number 12. Well done. Well done. Glad to see a few people still with me. Excellent. Okay. Fantastic. So I've got my number 12. I've saved that. Let's say I'm going to move my, if I move this over down to this next one, I've still got this node. This node is still actually here. It's just that I'm now pointing to something else, my top. I've also now kind of lost where this node is because it's floating about in a particular part in memory, not in my neat structure. So how do I really want to get rid of that node. Who remembers how we get rid of the node? How are we going to kill the node? Yeah, we're going to free that node. Okay, so at some point I also want to free that node here that used to be the top one. Excellent. But what's going to happen? How can I free it after all of these things happen? I'm going to run into some problems here because I don't know where it is. If I've moved it along, then I don't know where that node is that I need to free. And if I free it before I move down to the next one, then I'm going to have no idea where to move down next to. So I need to have something exactly. Brendan's got it. I need to make a temp before I free it. So that I'm able to, to free it without losing any of the information that I have going on. Okay, so let's say I have a struct node, and let's say I'm going to call it a temp pointer, and I'm going to point it to my top node, okay, because that's now going to give me this node here. And then I can play around with that because then I can free that after that. Okay, well done. Let's see how it might work in code. Okay, so we've said that we're going to create a temp node that we're going to keep our S top. Okay, so what that means now is my temp also has the same address. So this is my temp as well. Okay. Okay, so now I want to say that my int pop number is going to be my temp pointer data, okay? So what happens is this 12 is now going to go into the pop number variable that I've created here. And fantastic, okay? So now I want to move things along. I want to make my S top next, okay? So I'm going to move it along. So I'm going to move it down. So I'm going to move my S top from being over here, going down to the next one. So what that means is my S top is going to be equal to S top next. Okay, so I've moved it down one. Now, if I'm about to get rid of a node, I'm also going to need to change the size of this stack, okay? Because the size is going to reduce by 1 as well. So I'm going to reduce it down by 1. And that means I am now ready to free. So I'm going to free my temp. And that's it. Oh, I got too excited. I wrote it here, but I should have really, if I'm going to go with my comments so that you can look back on this, I'm going to put it here. Okay, so I've freed it. And then I'm going to return the pop number that was stored in here. So I'm going to return this because it's returning an int. So it's return. Oh my God, just doing whatever. Okay, excellent. So we've now maybe popped off the stack. We'll have to do some printing to do whatever's happening. Theo, if we had 3 nodes and you wanted to free the middle node, how would you do that? You can't because it's a stack. So in a stack, you always free only the top one. You only ever have the top node accessible to you. So only ever this is accessible to you. Only ever if there's one more on top of it, that's the only one that you can access. You can never access the middle or the bottom. You can't access anything else. That's how a stack operates. Last one in is the first one out. Okay, so then the stack, if I want the size of the stack, all I have to do is really return the size. So it's quite a simple function, isn't it? That's fun. You were able to do that in about 2 seconds. Okay, so now let's print the stack so we can see if what we're doing is correct. So I'm going to set the current node to head. So struct node current is equal to, and remember the head is inside my S top that holds, so inside my stack, the top element is the one that holds the actual numbers. Neil, excellent question. You can pop off until you reach the data that you wanted. You can. You absolutely can. Keep popping until you get to a number that you want or until you get to a value that you want. Yes, you absolutely can do that. Okay, so we set the current to the top, to the head node, which is located in the stack in the top. And while current is not equal to null, oh, that feels off. Look at this indentation. My goodness, that's lost marks. Okay, printf the number and then move it along. Okay, and then if we were to destroy the stack, okay, if we're going to destroy the stack. Now remember, every time we pop off the stack, we are destroying the node that we're popping off because we're using this free. Okay, so all we have to do is we have to keep popping the stack until it's empty to be able to pop all the elements off the stack. And I've got inside my size, I have the actual number of things in the stack. So I can say, whilst the size of this stack is not equal to 0, I'm going to keep popping off, which means that I'm going to be killing these nodes that are inside it. And all that means is at the end, I just have a blue container left that I want to kill as well, which means I'm going to free the stack itself. So I'm going to free whatever memory was allocated to my stack S. I'm going to free it as my last hurrah. And then that means that none of it is now happening. None of it is, none of it survived whatever was happening. So let's see what happens now. Okay, so we're going to do DCC and we're going to compile main.c and we're going to compile stack list.c and I'm going to call it a stack. So that is such a good question. Well done. Do we not need to decrement S size? So the only reason we don't is because I decremented inside my pop stack. So as soon as I pop, I decremented by 1, which means I don't have to do it in my destroy stack function. Okay, back to here. Okay, so we should have 11, 12, 13, 14 pushed onto the stack, and then I'm going to pop twice. I'm going to pop 14, and then I'm going to pop 13. Okay, the moment of truth. Okay, so first stack, we're going to push 11 on, push 12 on top of it, push 13 on top of it, and push 14 on top. So now 14 is sitting on top. So with the first popping off the stack, the 14 becomes popped off, and the stack becomes 11, 12, 13. The next pop that you do off the stack is 13 because it's the top number in my stack, the last one that I pushed on, and 11 and 12 is left on the stack. And I can keep popping until I get to the end. And I can destroy it as well. But obviously there's no way to see that you've destroyed it. I mean, you could see if you destroyed it successfully by then trying to access that space of memory and having an error. But there's no visual way to see if you've destroyed it properly. Okay, how is that on the stack using a linked list? How does everyone feel? Is everyone exhausted from that? Someone asked, will freeing the stack remove the nodes within? No, because remember that the nodes when I create the nodes, I'm alloc some space for the nodes. So every time I push onto the stack, what I'm doing is I'm mallocing some space for each new node. So each node, so what it actually looks like is this, okay? I've drawn it inside the stack, but the structure actually looks something like this. So when I create my stack, what happens is I've got this lovely stack here, okay? So this is my stack S, and inside stack I have a top and I also have a size. Now this top one is actually a node, okay? So it's going to keep the top node in it, okay? So it's going to have a structure of the top node and then it's going to have my nodes happening, until it reaches to null. Oh, you can't see what I'm drawing. That's really unhelpful. I forgot to move it down here. So I have a stack that has a top node and I have a size. And then the top node is my nodes link through from that top node. And the top node is the head of the thing. So Becky's asked a good question. What's the difference between the top and the head? There is no difference to it at all, except for in a stack, we refer to the head as the top node. but they are the same thing, exactly the same. So, you know, if you're writing your own code and you don't want to confuse yourself, you could easily write head in there. But top is just what we call the top of the stack. So then that's why we're just using that terminology. Yeah, great question. Well done. Okay, any other question about the linked list implementation? How do we feel about implementing it using arrays? You haven't touched arrays for a few weeks. How do you feel about that? Do you feel strongly about doing it or not so strongly? Anyway, let's try it. Okay, oh, Sean's asked a question. I don't understand why new node next is equal to stop in push stack function. In push stack function, new node next is equal to Thea's like saying no thanks for that array implementation. I have to say that array implementation is actually, it's a little bit messy. It's much easier to implement a stack using linked lists, but yeah. When you pop off a node, does it disappear or exist somewhere? I free it, which means that I kill it. I free it and I kill it. Okay, and then back to Sean's question. Sorry, there you go, got distracted. So, okay, why new node next? So we're on line 54 is equal to stop. Okay, great question, well done. Okay, so the reason for that is if I'm pushing a number onto the stack, okay, I'm pushing it at the head of the stack. So what I'm doing is I'm saying whatever node that I've created, I need to insert it at the head of my list, okay? Which means that it gets inserted, this is my head here. My head is this one here. And that means when I insert my new node, I'm saying my new stop is going to be the new node. So this is the new node. And then my new node is going to point to the old head. Please let me know, Sean, if that makes sense. It's because you're inserting at the head and stop is the head right now. Arrays, that reminds me of the good old days. Yeah, absolutely. Okay. Yeah. I mean, arrays are easier in that it kind of makes more sense what's happening, but it's just not as neat an implementation when you do it with arrays. We can start it so you can see what it looks like. You don't usually implement a stack using arrays, but you can, depending what the question wants and what's faster and easier to do. Again, that's the whole point of having just the header file, and then you leave it open to choice how you're going to implement the stack. Okay. How exciting. Let's do the array implementation. I sound thrilled about it. No, I don't mind it. I think it is okay to understand. Okay. Let's draw it out because that will make it easier to understand. Okay, let's say, and let me remember to move it, okay? Let's say I have a new stack, okay? So I'm going to, inside my stack, I want to have an array, okay? And then I might also have the size as well. So I'll have, this is my stack S. And I've created this stack that has an array inside it where I'm going to store all the numbers. So back to the good old days where we can use indexing to access things. Fantastic. Okay. Okay, so we will do the same thing in that first we will create our stack and then we want to push some numbers onto it. So let's say the first number we push onto the stack is 11, which means we'll place 11 in. Then we want to do 12. Okay, fantastic. We're going to move 12 into my array, or your array, or our array even. 13. Okay, I'm going to move 13 into the array. And 14. Great. I'm going to move 14 into the array. So what that means is that I want to keep track of this index here, because this index will give me how far we've gone up to. So it will give me the top of the stack. So the last index is where the top of the stack is. And when I pop off, I want to start popping from that index. So if I pop off, I want to pop 14 off first. So from the last index where I filled in. So let's have a look what that looks like. Okay, let's define our stack again. So we've got two things in our stack as I drew it. I've got an array in here, and the other thing that I have is the size, but really it shouldn't be the size because what I said is I need to keep track of where I am. So more useful is to have the index of the top item, because what that will give me is the size as well anyway. Okay, so I'm going to have an index and I'm going to call it top because that will give me, again, the index of the final item in there. So in my stack, I'm going to have an array, so an array of ints, so stack numbers. Oh. And I believe in my stack.h, I had a hash define of max. So I'm going to use that to create my array. And so you can see now, even though I'm only going to use up 0, 1, 2, 3 in this tiny little stacking that I'm doing, I'm actually going to have, 100 spaces for 100 things in there. So it's not as useful in terms of memory, and I can't really check if I've run out of space in that stack. I'm a little bit, I can't really do much. Okay, and so then I'll also have access to the top. Okay, so I've defined my stack. Now let's see what happens if I want to create some stack. Okay, so if I'm creating the stack, I want to allocate some memory just to that stack, and inside the struct stack is going to be my array, and also I'm going to keep track of the last index. So I'm going to do it the same way. Struct stack, new stack, and I'm going to malloc some memory for it. And what it will do is it will create this border around my stack S. So it will give me this bit here. So it will create an empty array in there and the int top as well. So I'm going to malloc space. Semicolon, actually. Okay, check that there was enough memory to create the stack structure. So again, I've checked that there is enough memory, and I do it in exactly the same way. So if a null pointer was returned from that malloc excursion, then there is not enough space, and I'm going to exit out of it. So again, I'm going to check if it's equal to null. I'm going to exit out of it. And now I want to initialize my stack. Okay, so in my stack, I have my array, which is where I'm going to be pushing numbers into, but I also have this thing called the int top, and I'm going to initialize it to be equal to 0. So what I've done is I've said that my top index is equal to 0 because I haven't actually moved any numbers in there yet. So I've initialized it to the 0th index. That means that my top item is sitting inside index 0. Okay, I return the new stack. And now I'm ready to push items onto the stack. Okay, so the first thing I want to do is I want to check that there is enough space in the stack array to push a new number onto. What that means is if I have gotten to the end of my array and my array is 100 elements, that means I've run out of space, okay? And I can't put in 101st element or even because indexing starts at 0, I will not be able to put in anything at index 100. So I need to check that my new stack, so my stack, and I've called it a new stack here. So I'm going to check that this new stack that I've been given has enough space for me to do things with. Okay, and if you remember, we're keeping our indexing inside the top. So my new stack top, that's got the last index that I have. Now, if that top is equal to 100 or it's equal to the max, because remember indexing starts at 0, so it's only going to go to 99. If it's equal to the max, that means I cannot actually push because push exceeds the maximum stack size. I can't really get it in. So I'm going to exit out of it and can't really do much after that. Otherwise, if there is space inside my array, I'm going to actually push the item into the array. Okay. So what that means is I'm going to access my stack and I'm going to access the actual array component of my stack, and I believe it was called stack numbers. Okay, and then I'm going to place something into it. So I've initialized it to be the top component because I'm pushing things always at the top. So new stack at the top, and that's going to be equal to the item that was sent to me to push on. So whatever was given to me here, that's the item that's going to go into the top index. Okay, and then I have to modify my new stack top. So my new stack top index, because I'm going to increase it by 1 because I've added an item on, which means that I can now increase my index by 1 because I've added an extra thing into my array. And that should hopefully push things onto the stack. Okay, let's see if we can pop it off. We've got a few minutes, so we're going to pop things off and then we're going to print it out and see if that works. Okay, so let's pop. Okay, we've got a boundary case again. What happens if the stack is empty and there's nothing to pop off? That's a good thing. So that happens if my new stack top is equal to 0, doesn't it? So if my top index is equal to 0, then that means that I'm not going to be able to pop anything off because there is nothing to pop off. So if this is equal to 0, there's nothing to pop off the stack. Stack is empty. Otherwise, I'm going to start my popping. Now, popping is a lot easier because you don't have to, destroy nodes and, take care of things like that. All I'm going to do is I'm going to take the top number. So new stack top. So whatever is sitting at my index is going to be, my top index is going to be the item that I'm going to pop off. And I'm going to also decrease my top index. I feel like I should have given it different variable names now that I'm looking at it. Okay, so I've decreased my index, and what do I want to return? I want to return the top item that was pushed. Okay. Yeah, I haven't used good variable names, have I? It's too much. Okay, so I'm going to return at my top index. And let's see if this works. Okay, so the only other one really then we need to do, and I think I did the print stack for you. Almost I did it so that we can see that it works. So in this case, I'm going from I until my new stack top, which has the number of the last index. So new stack top, and I'm going to print it out. And what am I printing out? I'm printing out my new stack, accessing the array. That's not what it's called. And accessing the array at index I, and then I'm just going to print it. All right, let's see if it works, and then we're going to wrap up. Don't worry, you just have to understand what a stack is in a very abstract way, dare I say it. Okay, and let's run. That's not what it's called. Okay, so I've got 11, 12, 13, 14. It's popping 14 off. 11, 12, 13 is left. I'm popping 13 off, and then 11, 12 left. Okay, so that's using arrays, but you really have to draw it out to use arrays in sort of a way that makes sense. It is easier to do it in a linked list. Well, I think someone will probably think it's easier to do using arrays. I don't want you to stress. You don't have to be able to implement it in many different ways in your exam or anything like that. You just have to really understand very basically what a stack is. It will be useful for your future courses. Maybe a few very short questions about it in the exam, but not you're not going to have to code out to some degree a stack, but you will sometimes use a stack in solving your problems. Okay, will there be no lab questions or tests in week 10? That is a very good question. There is lab questions in week 10. However, what we're doing is we are structuring them like an exam to give you practice of the exam environment. So we're going to make a few questions available to you, kind of like almost a practice test. They're going to be very similar to what you will get in those numbered questions in the exam as well. So that lab 10 is going to have, I think, an example of a question 1, example of a question 2, an example of a question 4 as well for you. So you'll be able to get a feel for what the exam will be like. Will you have theoretical questions in the exam? Not really. Not to that extent. It's going to be mostly quite practical. Neil, if there's no memory for a stack and we add to that stack, does that mean it's a stack overflow? Indeed. If you try and add to the stack when there's no more memory to add to the stack, you're going to overflow. And Faisal. So what we want to do is we'll make it available probably until your final exam so that you can have, a chance to kind of go back and forth and have a look at things. And what I'll do for next week as well is I will make the front page of the exam available in one-page format so that you're not, constantly going to the practice exam to see all the details as well. Does the exam have auto test? It does indeed. So you will be able to auto test, absolutely. And Catherine, why didn't we have to initialize the stack numbers array? You could have initialized it. We should have initialized it. It's very good practice to initialize it. So that is very good pickup. You should absolutely initialize it to be empty. Will we get practice exams apart from the lab? What we will get is some revision stuff that you will be able to go over. So there will be revision exercises that you'll be able to do. That one of the best ways you can revise for the exam is to do the labs and the weekly tests again. And where you had mistakes, try and do them again, without looking at your answer, and then you can look at the answers. So try and especially go, back to the beginning, see if you can do it all again nicely. But we'll talk more about it next week anyway. So Tuesday lecture, I plan to talk about the exam, and you can ask me any questions about the exam. And then the Wednesday lecture, we're going to really focus on doing a lot of revision questions. So I'll go after this and I'll make sure the poll works so you can actually vote for what kinds of examples you want to see. Okay, if there's no other questions, I'm going to wrap up today. Just one more day left of new material. And to make you feel better, this material is, introducing you to things you will need to know further on down the line as well. So please just try and have some basic understanding of it. I want you to really focus on linked lists as well, and your assignment. And if any questions, don't forget there's help sessions, there's lab times, and there's the forums. Please ask questions if you're not sure about anything. We will answer them. All right. I will make that poll available so you can vote as well. Thank you all so much for tuning in. I know week 9 is getting a bit intense to be able to keep up with everything. So well done on still, being able to function. And I will see you all tomorrow for another exciting look at a few other things like recursion. All right, see ya.